Hi, this is Dr. Jones. Let me walk you through Lab 1, the number sequencing computer. What you need to have already done, you need to download and unzip this NSC archive. By that, what I mean is, if I go over, so for example, what I've done is gone to my users bjones documents ECE3724 and created myself a directory called Lab 1. And then under that I put NSC altera, and then inside here are all the files that you'll need for the project. You'll have fewer files, don't be worried about that. Primarily we're interested in the QPF and some related files. One extremely important note, if you notice, there are no spaces anywhere. This is not lab space 1, it's lab 1, and not ECE space 3724 or my space documents. It's just documents because here I am on Windows Vista. I just gotta love it. If there's a space in your file name, it will not work because it's old kludgy software and that's the way it is. So if you have to, put it in // ECE3724/lab1 or whatever, but do not allow yourself to put a space in the file name because it will crash and burn in weird and unexpected ways. Okay, so unzip everything and we'll get started. Now, of course, before we go any farther, make sure you've installed Altera Quartus. In particular, you need version 10.1. That's what I'm using, or higher. We hope it'll work with later versions, but certainly this works with version 10.1. There is a DVD in the lab to save you from the joy of a 3.6 gigabyte download. You'll need to install both the Quartus 2 Web Edition software and the Model Sim Altera Starter Edition. Both of those are required. So of course what you've done now is you've clicked on the tutorial video link, and what I'm going to do is start at the beginning of this list and just walk you through this to try to save you time and get you really started on this lab. So we're going to start with step 1. Let's open the existing project. Here on my desktop I've got a handy shortcut. Notice my PC actually has a 32-bit version of Windows installed. Make sure to pick the 64-bit version if you got a 64-bit version of Windows, but go ahead and start up Quartus by double-clicking on that icon like I just have. It'll take a minute to come up. You can't see it on my screen, but there's a little X toward the top of this dialog box. I'm just going to click on that to get rid of it. And now we're actually ready to use the software. As I said, the first is to open that existing project, so let's do that. Here on the file menu there's a file open. You don't want that. Here we go, open project, because this is a project we're going to open. And then when that dialog box comes up, navigate to where you've stored your project. Again, in my case I've got it in this ECE3724 Lab 1 NSC Altera directory, and pick the nsc.qpf file and click Open to bring in that project. Next, let's get started on step 2. Let's take a look at the files that we have in the existing project. To do that, notice the 3 tabs here, Hierarchy, Files, and Design Unit. Click on Files. That's the way that I prefer to navigate this software, and then you can simply click on things. Here's the top level schematic that ties everything together, nsc.bdf. Now I'm recording this at limited screen resolution, so one thing you can do depending on the laptop size of your screen is move things back and forth a little bit to enable you to see better, and likewise I can do that top and bottom. I'll shrink stuff down just to try to give you a bit of a better feel for what we have. One thing you can do if that's helpful is you can do a view fit in window so you can see the entire schematic. I know at this resolution on the limited monitor size that's not helpful. Hopefully on your screen that's a little bit more useful for you. However, the overall design should be somewhat familiar. Let's take a look at the slides we've been talking about in class. Here's the final hardware from slide number 24. If you notice, we've got control logic here, a couple ands, an or, and a not. And over here, I'll zoom in a little bit so we can see that better. We have similar sort of stuff. Here's our control logic, the 2 input bits coming in here called MQ5 and MQ4. Here MEM4 and MEM5 coming into those gates, propagating through the logic, moving over here. Here's that inverter that showed up right here. So this is our control logic. Here's the counter that acts as our program counter, a data, a load, an increment, and a clock. So of course we have a data, load, increment. Here's the clock. R is for reset, and you'll notice a reset at the bottom here. There's a memory and it's labeled my ROM in this design. So here's our memory. And last but not least, an output register. So here at the top we have the output register. Now notice how things are connected in the schematic. In the simpler diagram, wires connect everything. When you draw schematics, you can use names to connect things. For example, you'll notice here we labeled a bus MEM, and in the design, and that bus, even though it's not connected with a wire, simply by giving things the same name, over here the label MEM3 to 0 will connect that in just the same way. So here's our nice little label MEM3 to 0. So those are connected even though there's not an explicit line between them. Okay, so we've got the basic schematic. This is the top level schematic that corresponds to what we've been talking about in class, as you can see. Now the next challenge is, let's go and take a look at how is the program counter, just a counter, the memory, and this output register implemented. To do that, there's a couple different ways. One way, I'll pick the arrow, I can double click on something. Here's my output register. I'll double click on that, and notice here I am at myreg.v. I can also see it right here. This is the output register, and here's actually the code behind it. This is the Verilog that creates an output register. Likewise, here's our program counter. I'll double click inside that. Will let us look inside that. Most relevant for you in completing this lab is, here's the code that your processor is going to run. A double click of that goes inside the file myrom.v. I could also double click here to access that file. And here's where at address 0 it outputs this data. And as you know, that is broken into two top words. That's the instruction 01, which is a jump conditional, and then it's jumping to address 0100, which is location 4. Notice that local here is at address 4, so this is a jump conditional 4, and out to the side we put comments because otherwise the bits are not very human readable. Okay, so we've got all that down. This is what you'll need to modify to change your program and put in your own ID number. There are two other files worth mentioning. The .vt file is a Verilog test bench, and this is where we wiggle pins at the input. For example, we tell it to take the clock, invert it, and assign that every 10 nanoseconds. So the clock will toggle, and we'll start out with clock at 0, reset at 0, and location at 0. Here at 5 nanoseconds, the reset pin goes high, taking the system out of reset. At 150 nanoseconds, the local or lock input goes to 1. So this is a way that we can wiggle pins and see what happens at the output. There's a do file that simply tells it to run the simulation for 1000 nanoseconds and show us graphically what the results are. So that's a quick tour of the schematic. Next, let's compile the design and also look at simulation. Step 3, compilation. Go up here to the processing menu and click Start Compilation, and you'll notice a window down. Here's the overall process, and you'll see as the compile progresses, different boxes get filled in. Takes a little while, so I'll go ahead and pause the video and come back when it's finished. When the compilation does finish, it will automatically launch the simulation for you. After the simulator finishes initializing, you'll get a somewhat disappointing blank screen. Not to fear. Let's just click somewhere in here and then click this zoom full button, and that'll show you the whole screen. And then you can click the plus button to zoom in well enough to see individual bits. I'll scroll out here to the beginning, and you can see that the chip starts down here. This is the reset line. Starts in reset. Low is a true reset. Here's not reset. The lock pin is low. That means it's not local. It's a long distance number, and you can see the clock toggling away. As a result, looking at the data that's being output, after a few cycles of going through that jump conditional, you immediately see digits coming out, 324, 8561. At this point, the local pin goes high, saying this is a local number. So after jumping back to the beginning of the program, we now just get an 8561 coming out of our state machine. So that shows you that the simulation demonstrates that this is working properly. When you're done with the simulation, be careful to actually close it. Click that X box and say yes. Otherwise, next time you attempt to run it, you'll get confusing errors from the software. Now, our next step, let's go and edit those Verilog files and analyze them for syntax errors. In particular, remember what the assignment is. We need to edit our Verilog code so it displays a 7-digit phone number. Looking at our design, as you recall, in here inside my ROM is the place where all the data is stored. In particular, it's fairly obvious from looking at the code what numbers it's going to dial. So let's do one simple modification. How about if we make it output 224? So instead of a 011, that's the number 3, let's make that a 010. That's a 2. And now we can simply compile and simulate that design again simply by hitting Start Compilation. It'll ask me to save my changes and then go through the compilation step and pull up the result. As before, I'll click Zoom Full and then zoom in enough so that I can see the actual design. And at this point, I'll see instead of the original 324, I'll get a 22. Notice that the number 2 is repeated, so you don't see a nice little cross there, but a 2248561, showing that really these changes do affect the file. Now, it's very easy to make mistakes. Remember to close the program as we go and change it. Let me show you what some of the syntax errors look like so you'll be familiar with finding and correcting those. So here we are in the ROM, and I'll just put something a little odd in here and go back and compile that. So I get a message, the compilation was not successful, there are 5 errors, and down here in the bottom I'll actually get a list of errors and it'll walk me through those errors. So let me go click on this error tab and it'll tell me there's a syntax error. Let me double click on that and it'll actually take me to the line and allow me to fix just that line and give me some hints. So often bringing yourself down to the error tab, double clicking on things, that will allow you to find and fix problems. After you finish that portion of the lab, it's time to upgrade your number sequencing computer to go from 16 locations all the way up to 32 locations. Now obviously the first thing you want to do is you've got something that works, copy it before you go any further in case you really mess things up so you can always go back and fix things. Now let's go in and change our design. In particular, we need to go and edit my ROM. Because we have only 16 locations, here inside the ROM, if I double click, you'll notice several things. First of all, the address is just 4 bits. Now that's good for 16 locations, 2 to the 4th, but we need a 32 location address. So there's a couple things that need to change. My input, this address pin, is now a 4 down to 0. And that means I need to bump up my address by 1 to reflect that fact. In addition, having changed that, my schematic needs to change. If you look at the schematic right now, notice it still says address 3 to 0, and I do want to bump that up to 4 to 0. Here's the appropriate procedure. First, here's the file that we've just been editing, my ROM. I'm going to right click on it and create a symbol file. And it'll ask me, do you want to save it? Obviously we do want to save it so those changes get made available. It'll tell us the symbol was successful, but you might notice to your frustration that nothing's changed here. That's because we also need to right click and tell it that we actually want to update the symbol. And I know that's just at the edge of your screen, but there's this update symbol block, selected symbol, and you hit OK. And now notice that address is 4 to 0. The symbol has been updated. And you might think that life is good and it's time to go and start the compilation and give everything a shot. But there are still some things missing. In particular, it'll give us some errors. It says, hey, wait a minute. The port said bits 4 down to 0, but the source only had 3 down to 0. So we take a look at the schematic, and sure enough, that says that address is a 3 down to 0. I'm going to double click on that. Why don't I upgrade that to make it 4 down to 0? So that matches. But wait a minute, that means that my counter needs to change because this is also a 3 down to 0 output. So I better go in here. My output Q is a 4 to 0. I'm also going to need it change it 2 places, at the output statement and the reg statement. And because I've changed that, but here in my schematic I haven't seen the changes, what I need to do is go regenerate it. Now this is my counter, so I'll click on my counter, create symbol files, yes to save. It'll create the symbol file. I'll just hit OK on that. Back in the schematic, it hasn't changed yet. Right click, update symbol, OK. And now that's a 4 down to 0. So I've got the address changed in all those locations. Why don't we go ahead and try it again? And this will notice that iterating on that process will keep helping us. Same sort of error. And notice what's blue. It's blued this, and it's also got a box around this. Aha! This needs to be a 4 down to 0 also. So the tool will help you track things down and attempt to fix all of those errors. So I do encourage you to kind of let the tool guide you and just be intelligent. Don't give up. Look at the errors. Look carefully around your schematic and find all those places where things aren't quite working as you upgrade from 16 locations all the way up to 32 locations. Notice that we have simply been following the instructions here in the lab. We changed that address bit to bring it up to a 4 bits. There's some other things. The data bus needs to be increased and the case statement needs to be increased. Here's another list of all those modifications. So I want you to carefully go through all those things. We mentioned modifying the schematic as well. However, I wouldn't want to spoil all the fun for you, so I'm going to let you find all those things in the schematic. Just carefully go through there and look. Don't just blindly search and replace things, but what needs to be changed and why should it be changed? There's definitely some subtle things in there. Make sure you catch those subtle things, because otherwise you'll get something that compiles but that produces odd results when you go and simulate it. I hope this has been helpful in terms of getting you ready for the lab, and wish you best of luck. Again, I encourage you to complete this as much as possible before you come to lab, rather than coming to lab and attempting to struggle through it. So do it now, and I again wish you the best.